Let me give you another example. An average degree of CR square root of log R, it suffices to force an arbitrary graph to have a KR minor. So a useful note is that every graph with chromatic number K has a subgraph of average degree at least K minus 1. So you see how just putting having some knowledge about your chromatic number can give you about some local structures. For example, saying that your subgraph has average degree greater than something. It means that your chromatic number is controlling almost the lower bound of your average degree. And you can think of that as your lovely k-partite graph. For example, 3-partite graph. For example, you have a graph that has the chromatic number is 3, so your average degree should be greater than 2. And these things are very, very interesting. Because you are not talking about a degree, maximum degree. You are not talking about minimum degree. But you're talking about average degree. Only when you have your chromatic number. And so it's very interesting. Now I want to talk about a lemma which has proved to be the cornerstone of all of the modern proofs of extremal graph theory. Because any theorem in extremal graph theory can be proved traditionally, just as we do in analysis and combinatorics, but you can do it much faster and much elegant by just using Szemerédi regularity lemma. And of course, Szemerédi, this Hungarian mathematician who got Nobel Prize in, I think, 2012. These Hungarian mathematicians worked on arithmetic progression on integers, but later people noticed that, and he himself, of course, he noticed that we can use it for modern extremal graph theory. Even Erdos, many of the theorems of Erdos, he didn't notice that they can be useful for graph theory, because his focus was just on numbers, and later people told them, you can use it for graph theory as well, and he was excited that his theorems can be useful for both number theory and graph theory. So the number of edges of G is x and y, and we define the density of a pair. I mean, x and y are just some. You see, for example, this is B, this is A, this is C, for example. So A, it has an independent set. So assume that this is a 3-partite graph, and A has a subset X, and B has a subset, for example, Y. And then you want to say that the edge density is almost similar. I mean, this goes to this, and this goes to this. So that's the definition of regular epsilon regular pair. So the edge density is defined as the number of edges between x and y divided by the potentiality that are very, very connected. It means x multiplied by y. So this is because this one is less than x multiplied y. So it says how much of your potentiality are you using to get succeeded. So it has a very interesting concept. So this is your edge density. And we say that if A and B, for example, are in V and X is a subset of A and Y is a subset of B, but you should notice that X is not small. It should be relatively large. This word relatively is used in this context because we want to say that it has some epsilon large, epsilon big. It's a relative number. And the cardinality of y, so y is relatively large. Then their density x and y is almost the density between A and B. So it behaves pseudo-random. It behaves like random. It means that, for example, you cannot find an edge here that has many. It has a very big degree, and very different than other vertices. So they should behave similarly. So they are kind of uniformly distributed. And so this is the definition of epsilon regular pair A and B. And you know that d of x and y, for the reasons I said, is just between 0 and 1. Because x multiplied y is your potentiality of become successful in this life, but you only use this number of edges to get succeeded. So your E should be very high, almost 1, so that you use all of your potentiality. It's like philosophy. So let's write regularity lemma, Szemerédi regularity lemma. It says that, Szemerédi I watched the interview of Szemerédi. It was very interesting. You must watch it in YouTube as well. And to know what is the motivation behind anything in graph theory. For every epsilon greater than 0 and positive integer m, there exists an integer m, and k is at most m, big M, and at least m. And an epsilon regular partition of vertex set of G into K sets. So we have a partition like this, V0, V1, Vk. In other words, very simple, I can say that it says that you can have some balanced partitions, some kind of balanced partitioning, and of course the number of vertices in each independent set is almost the same, at most 1. For example, you can have 5 vertices here, 5 vertices here, and then at most one difference. 4 vertices here, such that most of them are epsilon regular. For example, A and B are epsilon regular, but A and C are not. Or you can have much more sophisticated k-partite graph that each pair is connected, And most of the pairs, I mean, each one is a world, world of independent. It's an independent set. And you know that we want to say that most of them are uniformly distributed. I mean, between the relationship between each of them. Most of the pairs, for example, V1, V2, V3, because we are partitioning it, V5, V6. Most of them, so most of these sets are pairwise epsilon regular, but not all of them. So, for example, if V1, for example, is not like that, and V1 and V2 are not like that, so for example, V1 is the worst. I mean, it cannot be epsilon regular. Then I call V is the garbage bin. So, but most of them are epsilon regular. For example, here the edge density is 0.8, here is 0.7, here is 0.6. And so, of course, this one is better because they are better evenly distributed than, for example, other pairs. But the Similarity Dilemma, it says that you can find epsilon regular partition into k-sets, and the number of sets, of course, can be very, very bad because, and it's a bad news because the best bound is not an elementary recursive function, and it's a bad news, but k is at most m, so it's finite, and at least m. And the worst case, for example, could be, for example, you can even consider that each of these sets are singletons, only one vertex. This, you can imagine such a graph as well. That's why M, the big M, is at most the cardinality of G. And proof needs two lemmas. The first lemma is very simple. The second lemma I don't prove because it's very, very long. But using two lemmas, you can easily prove that. So there are two different definitions for epsilon regular partition, and they are equivalent. I mean, there is no contradiction or conflict between them. So they are almost the same definitions. One of them is from the book of Drisler, and the other one from that mathematician in MIT. I forgot his name. I think he's Chinese, but he's in MIT. I forgot his name, but so these definitions are almost the same. You can partition your vertices into V1 up to Vk, and it is an epsilon regular partition if the sum of Vi, Vj is less than epsilon V of G squared. Of course, the summation is over all of the pairs I and j such that Vi, Vj is not epsilon regular, because we are interested in the worst case, to bound the worst case. If they are epsilon regular, it's okay, it's fantastic, we are happy. But we are not happy if they are not epsilon regular. That's why we put this bound over that. So if all the cardinality of VI's are roughly the same as V of G divided by K. And the similarity regularity lemma, we can say that every graph has an epsilon regular partition into at most m, as I said. So we have m parts, and a good remark is that we can make a partition equitable, equipartition. So all of the cardinality of all of them is the same, except by one of them. As I said, for example, you have 6 vertices here, 6 vertices here, and we have 5 vertices here. And this is the three-partite graph. And so let's go and define energy argument. I mean, the theorem can be, let's rewrite the theorem again. The theorem of Similarity. It says that, Szemerédi says that for any epsilon and for there exists an M such that every graph has an epsilon regular equatable partition of vertex set into k parts. So we have k parts. The lower bound is M. The upper bound is capital M. So what is the energy increment argument? What is the energy increment argument? So we start with the trivial partition. So all of them is just ones. So we have one cluster, and all of the vertices are inside that. And then the algorithm is like this. While a partition is not epsilon regular, so we are doing it until all of them becomes epsilon regular. So while it is not epsilon regular, for each pair Vi and Vj, which is not epsilon regular, we can find a superscript ij is a subset of Vi, and Aj is a subset of Vj. We witness. So these sets are witnessing because they are not epsilon regular. So we have a witness of that. They are witnessing or witnesses non-regularity. And so we simultaneously refine the partition using all Aij. And this is the algorithm. You can implement it in Python. And why does the process stop even after a constant number of steps? This is the problem. Why does it even stop? And that's why you need to understand the notion of energy of a partition. Energy of a partition. It's almost the same as the concept of energy in machine learning in the context of graph theory, I mean. It means that at each step, energy increases. Energy increases when you refine it, because at each step you are refining it. And it's at least C of epsilon. And so we want to define that for any U and W as a subset of your vertices, the energy of U and W by definition is just the cardinality of U times cardinality of W divided by n squared. The density between times density between U and W squared. So for partition PU, we have, for example, PU partition and PW partition. In PU partition, we like to partition as an intersection of U1, U2, UK. So this is P of U. And we can partition U, W, we can partition as W1, W2, WL, and this is PW. We can partition W as well. So we have two sets, U and W. We partition U like this, we partition W like that, and then we say that now we can define the energy of partition U and partition W to see that the energy of pairwise subsets.